but I'm recording now. All right, so this is, you said 8.6. All right, what do you think? That's not a horrible answer.
But it would not. It would be less stable.
Yeah, but it's weaker. It's weaker than the first one. You follow me?
Right.
We're going to talk about that too. I'm going to introduce that in this section about how much more acidic one acid is than the other. All right. What about here? Let's do D. It's 8.9 times 10 to the 7th. And we're doing negative log of that. What do you got? It should be almost about 3 times what the other one was.
It's negative 7.9.
Yeah, so about 2.5, close to 2 times. So the pKa you said is negative 7.9.
Yes, sir.
Okay, good. So that's how we interconvert between those values, right? So you should be able to do number 4. Number 4 says convert pKa into Ka. How would you do that? Remember the log is base 10, right? So it'll be 10 to the what? Minus pKa will be equal to Ka. Is that right?
Yeah.
So that's what you would use for that. Following?
Yes.
Mm-hmm. So that's how you would interconvert between pKa and Ka. Let's do this though. I want to introduce another concept here. So I'm gonna ask this question: if you have an acid with a pKa of negative 4.5, and then you compare it to an acid with a pKa of 8.6, right? How much more acidic? Brain moving faster than my hand. I'm gonna call this A, and we'll call this B. It's A and B. All right. So there's a way to do that. If we take the difference in the pKa, right, and we set it equal to the log of x. X is going to be, I'm trying to do that. X is going to be the number of times more acidic or less acidic or whatever, right? So how would we solve that? How we solve for x? It's just like what we did up here, right? So it would be 10 to the difference raised to the difference in the pKa is equal to x, because the log is base 10. Okay. So the difference in the pKa, we're just gonna take the absolute value of that, because you don't want that delta pKa to be a negative number, right? So it sounds like a lot, but it's really not. You just take the difference. So it'll be negative 4.5 minus 8.6. What is that? 13.1. Is that right? We're taking the absolute value, so that's why I just left the negative sign off. Is it 13.1?
Yes.
All right.
Yeah.
So in order to find out how many more times acid A is, more times acidic acid A is than acid B, we're just gonna stick that number in here. So it's 10 raised to the 13.1 equals X. Somebody put that in your calculator. Tell me what you get. It's a lot. What is that? A billion, trillion? Is that right? 10 to the 12th is a trillion, yes? 6, 12. Yeah. Should be a
I got 1.25 times 10 to the 13.
times 10 to the 13th power.
Yeah.
Yeah. That's a lot. that's a trillion, that's almost over a trillion times more acidic, right? What that means is that for every one proton that acid B gives away, are you following? Because you know acids give up H plus, right? For every H plus that acid B gives away, acid A gives up 1.25 times 10 to the 13th protons, right? It's that much more acidic. So that's what it means when you ask how much more acidic is one acid than the other. Are y'all following that? Anybody not following that? Say
Yes.
something. Feel free to take yourself off mute unless you're having another conversation about something else. All right? Everybody okay with that?
Yes.
Okay. All right, let's go back up here. I want to touch on number 7 real quick, because 7 is going to lead us into our discussion, what we're going to discuss on Monday. Then we're going to go back up top, right? So one of the things about strong acids, weak acids, all, pK, low pK, high pKa, right? When you're talking about an acid being stronger or weaker, remember we talked about this on Wednesday, it's really based on how stable the conjugate base is, right? It's based on how stable the conjugate base is. And so the conjugate base is what? Somebody tell me what the conjugate base is in an acid-base reaction.
A proton acceptor.
That's a Bronsted base.
Acid minus hydrogen.
Never mind.
The conjugate base is the acid once it loses its proton, after it donates it, right? So if you look at A, I'm gonna draw this on another sheet. I don't know if I can cut it and paste it down there. Copy. Let's see. Paste it on this blank sheet right here. Oh, that's perfect. Because I don't want to try to squeeze all that in on that other page. All right. So let's look at A. What would the conjugate, first of all, we need to figure out which proton is acidic, right? With a carboxylic acid, it's this proton that's on the OH. Are y'all following that? Because that's one of the things about acids and bases, one of the skills is that you got to be able to identify what the acid is and what the acidic proton is. So what would the conjugate base of that look like? Let's say I added in some sodium hydroxide. Right? And I grab this proton here, and I'm giving that other pair of electrons back to oxygen. So it will look like this. This will be the conjugate base, right? Following? If you're not following, say something. All right, that's the conjugate base for A. And then the conjugate base for B will look like this. It's the same conjugate base, right? But the bromines are down here. All right. So the question asks, which is more acidic? Let me write that question down here. And we don't have any pKa values. Is that okay? All right, so we have no pKa values, but we have to answer this question about which of these acids is more acidic, which is the better acid. So there's another way to think about it. And again, everything is going to come back to conjugate base stability, right? Right? So when we talk about conjugate base stability, what we care about is where are we putting our electrons in the conjugate base, right? Because again, if the conjugate base has a charge, then I need to be able to, there's a magic term we learned a few weeks ago. I need to be able to take those electrons and do what to them? How do I stabilize electrons and charges?
With resonance,
I can do resonance, which is a form of what?
deprotonation.
I think you own it now. I heard it. I heard it come out. Hold on, I gotta plug this laptop in before it dies. Did I hear you say something about delocalization? Is that right?
Oh no, I didn't say that. I said something.
I heard somebody say that. Right, but you stabilize electrons and charges through what's called delocalization. All right, everything is going to be based on that. Right, delocalization. It's going to come up at some point. If it ain't the Wi-Fi, it's the computer. If it ain't the computer, it's the iPad. I'm gonna start teaching using smoke signals. That might work. Then the wind will blow and screw that up. All right. So you want to delocalize that charge, right? There's a bunch of ways to do it. The way I normally teach this is with a mnemonic. I use the mnemonic HIRES. So hybridization, induction, resonance, electronegativity, and then size. All right. I'm just introducing this one problem. Then we're gonna go up and do some arrow pushing. But I want to whet your palate for Monday because that's what we're gonna be talking about on Monday. All right. So when you're talking about now, these are ways to delocalize charge or delocalize electrons. All right. So with hybridization, what do you remember about hybridization? Anybody? It's 3 states. Is that right? SP3, SP2, and SP. Is that right? Yes, no, maybe.
Yes.
Yeah.
That's right.
Praise the Lord. I thought everybody fell asleep. All right. What do you know about the hybridization state as it relates to electronegativity? Anybody remember that? Remember we talked about S character and 25% SP3 and 50% SP. Anybody remember that?
The
Yes.
So SP, let me just say that part. If it's SP, it's better, right? If you're comparing atoms and what you're looking at is the different hybridization states, SP is always going to be better because it has more S character, right? That means it's more electronegative. So an atom that has that's SP hybridized has more S character and it can handle a charge better, right? We already know about what resonance is. What is resonance? Anybody? Give me your definition of what resonance is.
Okay, I feel like resonance is basically trying to charge, like they're trying to share the charge.
So it's a sharing of electrons or sharing of charge through overlapping orbitals, right? We talked about that. And that's why you can only do resonance with certain patterns, right? Allylic anions, allylic cations, allylic radicals, so on and so forth. So resonance is, excuse me, sharing electrons.
Dr. Russell,
Yes.
resonance also like they have to spread out the charges on the atom so that it becomes more stable.
Yeah, absolutely. That's the whole purpose of delocalizing electrons through resonance is to stabilize the charge. You're absolutely right.
Okay.
Right. But that's a way to delocalize electrons, right? Through resonance. And then electronegativity, we know what that means, right? It's the atom's affinity for electrons. More electronegative atoms stabilize charge better than less electronegative atoms, right? And then for size, larger atoms stabilize charge better than smaller atoms. Right? Because keep in mind, all of these are in reference to the conjugate base. You following? So if I'm looking at the conjugate base, what I'm looking at is the atom in the conjugate base where the charge is. And I want to know if that atom can do resonance. I want to know how electronegative it is. I want to know if it's what the hybridization state is. I want to know what the size is when I'm comparing acids. All right. So, and then with the induction part, induction means that you have some functional group close by that's electronegative. So I'm going to summarize that because I don't have a lot of room to write. Right, so you got an electronegative group that's close by. What does that mean? If there's an electronegative group close by, it can polarize a charge. It can pull some of the electron density towards itself. Right, so it can create some polarity. Are we okay so far?
Yes, sir.
All right, let's move back to the example. So now we don't have any pKa values, but we do know what the let me get this out of the way. All right, we do know what the conjugate bases look like. So out of those factors that are there, look where the charge is. The charge in each case is on oxygen, and oxygen is sp3 hybridized. It is the same atom, so you're not comparing different atoms, so you don't have to worry about size or electronegativity or hybridization, right? Because each one of those atoms is the same. So it's going to have the same size, same electronegativity, and they're both in the same hybridization state, right? So what are we thinking now? There's only two factors left that's going to stabilize this. Is that right? What's one of them? Tell me what's one of them that what can I do on this functional group right here? Oh, man.
Can't you break up that bond that's on the O?
Who is that speaking?
Kristen?
Yeah, you can. You can do resonance, right? I can
Yeah.
take this pair of electrons and push them here, and I can take the pi bond and push it up on the oxygen because that fits into one of our resonance patterns. It's an allylic anion. Is that right?
Right.
Can I do the same thing on the other side?
Yes.
Yeah. So resonance can't be the only thing that's going to stabilize that. You follow me? Because they can both do resonance. Now, if one had more resonance forms than the other, that would be different, but they can both do resonance. So the only thing that's left is induction. All right. So when we look at this oxygen that's negatively charged, and again, induction is having an electronegative functional group close by a charge, right? Look at where the bromines are in each case. So here you have bromine, these two bromines down here. They're electronegative atoms, and then here your bromines are here, closer to the charge, right? Induction is based on proximity. The closer that group is, or the functional group is to the charge, the more it'll be able to delocalize that charge by polarizing. So what this is going to do is create a dipole in this direction, right? Because those electrons, if you think about it like any of y'all, I'm sure you have, you seen a dandelion before? How the little, I don't know if they're petals or whatever they're called, on a dandelion, how when the wind blows, it blows them off. That's how electrons are around atoms. They're like a cloud. And so if you put, or if you've seen like metal filings close to a magnet, if you put a group close to that electron cloud, it's going to start pulling that electron cloud towards itself. So the closer it is to the cloud, the more able it is to pull that cloud or disturb that cloud and move some of that electron density towards itself. Can you do that on the other side?
It's too far.
Too far away, right? So which charge do you think is going to be more stabilized?
First one.
The first one, right? A is going to be more stable because of induction. Right? And what causes the induction are those electronegative bromine atoms that are close to that charge, right? The further away you move those atoms, the less influence they have over trying to stabilize that charge. So this acid is going to be more stable. I mean, let me take that back. This is going to be more acidic. And the reason it's more acidic is because the conjugate base is more stable. All right, I know that was a lot, so ask questions. So the conjugate base stability and the acidity go hand in hand. If the conjugate base is more stable, then the acid is going to have a lower pKa. If the conjugate base is less stable, the acid is going to have a higher pKa.
So whenever we need to figure out which one's the stronger acid when we're not getting pKa,
This is
we
what
need
you use.
to draw the conjugate base and then.
Yep. Look at the conjugate base and then look at these 5 factors here.
Okay.
Right.
And we
And
can
see,
order by those factors, right? We can't just start from anywhere.
yeah, no, there's no order to them.
Okay.
I wrote it like that so you can remember them.
Okay.
Because it's a real word, right?
Yeah.
Yeah, I could have just given the letters in any order, but I figured if I put it in the form of a word that you could remember, then it will make it easier for you to remember what they are.
All right. Thank you.
Yeah. So, all right. Any questions about that example? And you can apply that it's the same logic in the example in number 6, right? You can see what the conjugate base is going to be. You can see that the oxygen here is pointed closer to chlorine than it is over here, right? So A is going to be the stronger acid here as well, and it's going to be based on the same factor. Right, it's going to be based on induction. All right, any questions about the example we just did? All right, let's go up and I'm gonna pull some of these examples from up here so we can work on these arrows. So I really want y'all to get in the habit of writing the mechanism out. So we got 13 minutes left. We're gonna do C and D. I'm gonna pull them down I'm gonna copy them and then pull them down to, actually we're gonna do all of them. And we're gonna predict the equilibrium too, because that's another skill that we need to have. there on a blank page so we can work through it with plenty of room. All right, let's do, that's not off the screen, is it?
No, it's fine.
All right, let's do, let's warm up with D, because D is pretty easy. All right, so I'm gonna write that out, CH3, 3H, and that's positive, right? Can somebody tell me why the formal charge on nitrogen is positive?
It only has 4 bonds.
It's got 4 bonds to it, that's right. Who was that?
Amaria.
Man, you stay eating lunch. Yeah, but you're right. It's got 4 bonds, and so it's going to be positive, right? So this is my acid, right? If you ever have a question about the OH, you cannot pull off that proton, that hydrogen from that oxygen. So don't ever think about that, right? That's never going to be the acid unless it's water. Then this proton can come off. But if you see OH by itself, that OH is not going to be acidic whatsoever. All right. So what's the mechanism for acid-base reaction? It's always from the electrons go from what? Base to the acid. Is that right? So I'm going to take this pair of electrons and attack the proton. I don't care about anything else on that acid except for that hydrogen. What's that called? What's the term for that reaction when I pull off a proton from an acid? It's got 2 names.
Deprotonation.
Say again. I heard it.
Is it deprotonation?
Yes, that's one term. What's the other term?
Is it heterogenic?
That's the description of how we make and break the bonds. It's proton transfer, right? So proton transfer or deprotonation, they both mean the same thing. So I'm going to give this pair of electrons back to nitrogen. On the other side of the arrow, did I write out? Yeah, I'm right. On the other side of the arrow, I'm gonna put a box here because we're gonna predict the equilibrium too. I'll have HOH and then CH3, 3N with a lone pair. Anybody not see that? All right. So now let's add another piece to this. Let's predict the equilibrium. How do we do that? We need to know the pKa's of the acid and what?
Conjugate base.
No, the conjugate acid. That's a good attempt, but the conjugate base is not gonna have a pKa because it doesn't have a proton to give up. So we need to know the pKa of the acid and the conjugate acid. We know the pKa of water. We looked that up already. It's 17, right? Either Amaria or Christina, is that right? Kristen, yeah. One of y'all give me the pKa for that ammonium, the trimethyl ammonium. Was it 10, 10.2, something like that? think it was 10.2.
Yeah, I think that's right from last night. I can't
Yeah.
remember. I can't find it online though.
Yeah, I think it's 10.2. We're gonna roll with that. All right. So which side will be favored? Because now, so we've done the mechanism, we've identified the acid and the base, we've identified the conjugate acid and the conjugate base. Now we can predict the equilibrium. We can say that the reaction is either gonna favor the products, which would be on the right, or the reactants, which would be on the left. So how do we know? Having the pKa's of the acid and the conjugate acid, how do we predict the equilibrium?
The seesaw.
With the seesaw in, it's going to tilt toward the bigger number. Is that right?
Yeah.
So when I put my equilibrium arrows in, the larger arrow is going to be facing the products, and the shorter arrow will be facing the star materials. Is that okay?
Yes.
Yeah. Let's add another piece. Let's add another piece, because this may help you to understand why the reaction always goes towards the weaker acid, because that's what we said when we talk about predicting equilibrium, that the weaker acid is always favored. So how many more times acidic is the acid than the conjugate acid? Help me out, man. And I'll speak out at once. So how much more acidic is the acid?
Is this just like the last one we did where we took the difference and then
So again, perfect. You take the difference in the pKa, right? So delta pKa in this case would be what? 17 minus 10.2, that's 6.8. Is that right?
Yes.
And then it's what? X, come on, finger. 10 raised to the delta pK. All right? Or 10, I'm gonna say raised to the 7. 10 to the 7. That's 10 million times more acidic. Is that right?
Yeah, I think so.
Yeah.
Yeah, 10 million.
Mm-hmm. That's a lot. So why do you think the equilibrium is gonna favor the weaker acid? Because the acid with a pK of 10.2 is giving up protons so fast that the conjugate acid, by the time it gives up one proton trying to go back the other way, the acid has already given up 10 million. You follow me? So that's why the equilibrium is going to favor that side, because the other side can't keep up. So that's why equilibrium always favors the weaker acid. So we've done the mechanism, we've predicted the equilibrium, and we've determined how much more acidic one side is than the other. All right, any questions about that one? We only got like 3 minutes left or so, but we could squeeze in another one if y'all want to.
so the pKa that was 10.2, that was of the original acid that's on the left.
Yes.
Okay.
Can we do another one?
Oh yeah, absolutely. Thank you for saying that, man. All right, which one? Y'all pick. Y'all want to do C, A, it don't matter, or B?
Can we
Uh,
see?
Do C.
C? All right, we can do C. I'm gonna draw it out, and then we're gonna go through the same process with it. All right, so here is benzoic acid. I'm drawing it a little different because I'm trying to keep the geometry intact. And then that's plus OH minus. And then that oxygen has 3 lone pairs around it and it's negative. It's probably got a counter ion hanging out somewhere, maybe a sodium or a lithium or something, something like that. And put the box in for my equilibrium arrows because we don't know. Let's do the mechanism first, right? This is my acid. It's a, what functional group is that? Anybody remember? That was actually it's on this test.
Is it a carboxyl? I can't pronounce it. The
Yes, you
carboxylic
can.
acid.
Yeah, it's a carboxylic acid. That's exactly right.
Okay.
So that's my acid. And then this is my base. So when I put the electrons in, boom, this is coming right here and attacking this proton, right? And then I'm breaking, let me put these electrons in. I'm breaking the OH bond, like so. Y'all following that? So what do I get on the other side of my arrow? Or on the other side of the reaction, I get H, OH. Is that right? That's my conjugate acid. And my conjugate base is this, right? Well, let me put the negative charge down here. And let's see if I can squeeze these lone pairs in. Come on, man. All right. So far, so good, yeah? Now, let's predict the equilibrium. Somebody look up the pKa for benzoic acid. Benzoic acid.
It's 4.2.
4.2. And then water, we already said is what? 17. Yeah? Let's put it in the seesaw. Which way is it going to tilt?
Towards the products.
Towards the products, right? It's always going to move, it's always going to favor the weaker acid. All right, we good with that? Now, the last part of the problem. Let me put the equilibrium arrows in here. Last part of the problem says, it's going to ask how much more acidic is benzoic acid compared to water? How do we figure that out?
Subtract the pKa's.
So 17 minus 4.2, what is that, 12.8? Is that right?
Yes.
So the number of times is 10 to the 13 times. I'm gonna round up. That's okay to round up, by the way. It's 10 to the 13 times more acidic. All right, 10 to the 13 times more acidic. That's a lot. All right, so what does that mean for the equilibrium? It means that for every 1 proton water gives up going in the reverse direction, benzoic acid is giving up 10 to the 13 times more protons going in the opposite direction. So it's going to always favor the weaker acid. Is that okay?
Yep.
All right, my iPad is on 1%, so I'm gonna stop sharing. Well, yeah, I can stop sharing because I can upload these notes. It won't be a problem. I'll upload them as a PDF. And I've been uploading the notes from every day. What I'm gonna do, I'll put the date, because it's the same handout. I'll put the date by what we did today. That way you'll know what you're looking at. Put it in pink today. All right. Any questions?